In this video, we're going to begin to look at some applications of Newton's laws. And before we do that, we need to talk about a few assumptions we're going to make. First off, we're going to assume that objects behave as particles. And so what that means is we're going to act like all objects have their mass concentrated at the center, and so we're going to ignore all rotation for now. Later, we will get into rotational dynamics, but for right now, we're going to say all the mass is at the center and objects act as particles. And we're also going to assume that masses of strings or ropes or anything like that on a pulley are all negligible. And we're interested only in forces that act on the object that we're studying, and we can neglect all reaction forces. So when we're talking about a particular object, we only care about the forces on that object, not the forces that that object exerts on others. Many of our situations and problems will deal with ropes or strings, and when we're dealing with ropes, we're going to ignore any frictional effects of the ropes. We're going to ignore the mass of the rope, even though the mass does have a little bit of effect, but it's negligible. And the magnitude of the force exerted along the rope is called the tension. And we're going to assume that the tension is the same throughout all points of the rope. In actuality, this isn't true. However, because of our limitations with math, we are going to assume that all of the tension throughout the rope is constant. So when we attack application problems of Newton's laws, we need to draw something that's called a free body diagram. And a free body diagram is a diagram of the forces acting on an object. And this diagram must identify all the forces acting on the object of interest. If we leave any out, we're not seeing the true story. So we need all forces acting on the object and only the forces acting on that object. We want to choose an appropriate coordinate system, one that helps us out, typically one that has the origin at the center of the object, and we have all of our horizontal components aligned on the x-axis and the vertical components aligned on the y. If the free body diagram is incorrect, the solution will likely also be incorrect. Let's look at an example of a problem where we'd want to draw a free body diagram. So let's say we have the magnitude of the force T is the tension acting on the box. We have a person over here that is pulling a box with a rope, and we're calling T the tension force. We will say N is the normal force that the ground is exerting up on the box, and F sub G is the force of gravity that the earth is exerting on the box, which is pulling down. So when we draw the free body diagram, we say that the center, everything is coming from the center of the box, which is that point, and we draw the tension to the right, because that's the direction of our pulling force, which is the rope and the tension in the rope. We have the normal force going up, and we have the force of gravity going down. Now, we're going to pick to say that to the right is positive and up is positive. One of the reasons that we want to draw this free body diagram is that we see that we have an imbalance in force. Recognizing where the imbalance in force is, whether it's in the y direction or the x direction, will help us to solve the problems appropriately. So when we are solving Newton's second law problems and we have these free body diagrams, we need to read the problem at least once, and most of the times we'll need to read it several times. Drawing a picture is absolutely imperative. We must draw a picture of the system. It doesn't have to be a work of art, but we need a physical representation. We have to identify the object of primary interest and indicate the forces with arrows that are acting on the object. So these are just forces on the object. We are not concerned with reaction pairs unless our object has a reaction pair acting on it. And we want to label each force, use labels that bring to mind the physical quantity involved, such as N for normal, T for tension, G for gravity, so on and so forth. You can either use the letters, or if you want to use F to remember that it's a force, and use the subscripts to label. I'm fine with either way. So if you want to call the normal force N, or if you want to call it F sub N, I'm okay either way. Then we want to draw a free body diagram. If there are multiple objects that we're interested in a given problem, then we want to draw separate free body diagrams for each object. and choose a convenient coordinate system for each of the objects. It could be different for each object depending on the situation. Then we want to apply Newton's second law using the x and y components taken into consideration. We will have to use our vector addition, our vector components, and all that. And then we want to solve for any unknowns. If an object is in equilibrium, and keep in mind this could be just in one direction, meaning equilibrium in the x direction or equilibrium in the y direction. If an object is in equilibrium, meaning it's at rest or moving with a constant velocity, then we can say that the net force is equal to 0, or the sum of the forces is equal to 0. A lot of times this will help us to relate two forces together, to say that the gravitational force is equal to the normal force, or to say that the tension force is equal to the frictional force, so on and so forth. This will help us to relate two forces together, or possibly even write an equation of three or more forces. The main thing to remember is the sum of the forces is only equal to mass times acceleration when the object is accelerating. And so, as mentioned before, it is easier to work with the x and y components and look at the sum of the forces in those two directions separately. So sometimes you may have the sum of the forces in the x direction equal to 0. Sometimes it may be equal to mass times acceleration. Sometimes the sum of the forces in the y direction will be equal to 0, or sometimes it will be equal to mass times acceleration. Just a reminder, this could be extended into 3 dimensions. However, we are only going to remain in 2-dimensional space in this course. And a zero net force does not mean the object is not moving, but that it is not accelerating. Let's take a look at this equilibrium example and the free body diagrams that are drawn from it. So we have these two cables that are holding up a stoplight. And the two cables are at two different angles. We have a 37-degree angle and a 53-degree angle. And the stoplight is being held by just a single cable here. And so we have 2 points of concern. We have the stoplight. What are the forces acting on the stoplight? Naturally, we have gravity pulling on the stoplight. But we also have this tension number 3, that is pulling up on the stoplight to keep it in equilibrium. So since this stoplight isn't moving, at least we hope not, otherwise it'll be falling on a car or something, then these two forces have to be equal because those are the only two forces acting on the stoplight. Another point of concern would be this junction point right here, and we see that we have 3 forces acting on that. We have the tension down, so the string that's pulling down. We have the tension number 2 up and to the right, and then we have tension number 1 that's up and to the left. To treat this problem properly, we would need to break these two tensions 1 and 2 up into their components, and so we would say that this x component is going to be T1 times cosine of 37, and then the y component here will be T1 times the sine of 37, and likewise we can look at T2 and split that up into the components of saying that this y component will be T2 times sine of 53, and then its x component will be T2 times cosine of 53. And so that way we can see that, well, these two have to be equal since we're in equilibrium in the left, and then these two have to add together to equal this third tension force because it needs to be in equilibrium in the y direction. With problems dealing with objects in equilibrium, we will set the sum of the forces equal to 0. We will not set it equal to mass times acceleration because it is not moving. All right? There is no acceleration. We're in equilibrium. So we set the sum of the forces in the y direction equal to 0, and we set the sum of the forces in the x direction equal to 0. Keep in mind, we have some are positive, some are negative. So if we say that the right is positive and up is positive, then this component here is negative and this vector down is negative.